Now let us look our next topic, which is wedge constraint. So our next topic, we are considering wedge constraint. So as you know, wedge means inclined plane. So we want to study wedge constraint. That means we have to study constraint motion equation with regards to the inclined plane. So let us see the concept first. So in this case, let us first see normal constraint. Now, if we have two blocks, let us say this is block number 1 and this is block number 2. They both are kept on a horizontal surface. Now, suppose I apply a force F here, and suppose block number 1, this is block number 1, this is block number 2, moves with a velocity v1. Then for normal constraint, block 2, let us say it moves with velocity v2. Then we can say by normal constraint, the velocities of two blocks have to be equal. So this is the equation for normal constraint. v1 is equal to v2. Similarly, if the two blocks are accelerating with accelerations a1 and a2, then we can say acceleration of first block a1 equals acceleration of second block a2. So this is the normal constraint equation. Now, after this, let us consider another possibility. Suppose we have like this, we have a diagram. So this is ball and this is the ground. And suppose we have a block like this, and I cut this block into two parts. Let us say one of the block is block 1, the upper block is block 2. So let me draw the free body diagram. This is block number 2 and this is block number 1. Okay, so these are the diagrams. Now, after you understand the diagram, what is wedge constraint equation here? So if I apply wedge constraint equation or normal constraint, so then wedge constraint states that the components of velocities or acceleration perpendicular to the surface are equal. So let us say this block A2 moves with acceleration A2. This block A1, let us say in this case, A1 will be forced to move in horizontal direction. So A1 will be forced to move in horizontal direction. So in this case, we have like this. As block 2 moves down, this block 1 will continue to move in forward direction, in the rightward direction. So this is what we have. Now, if I consider the components which are perpendicular to the incline, so let us say this angle here is theta. Okay, so this angle here is theta. Now, in this case, the component of acceleration A2. So let me make the diagram more properly. Let us show a new diagram here. So this is block number 2. And let me draw block number 1 at a slight greater distance. Actually, they are in contact with each other. But just to make you understand, I am showing them far apart. So this is block 1 and this is block 2. And this has acceleration which is A2. This has acceleration which is A1. As block 2 slides down, block 1 slides in rightward direction. So now let us say this angle here is theta. So this is theta here. Okay. So in this case, this will be theta. And this angle will also come out to be theta. So we can say the component of A1 along theta is A1 cos theta. And the component perpendicular to this A1 cos theta is A1 sin theta. Okay. So this is the perpendicular component which I am showing here. Let me show this in yellow color. So this is the perpendicular component. If you can see, this is yellow color which I am drawing here. So this is the perpendicular component of A1. Similarly, the perpendicular component of A2, if I want to make by geometry, so it will be like this. Let me again come back to red color. So now in this case, This angle is theta. This angle here is theta. Let me make this diagram once again. So this angle is theta. Yes, now component of A2 in perpendicular direction is A2 cos theta. And along the incline, it will be A2 sine theta. But we are equating what? The perpendicular components. We can say by wedge constraint or normal constraint. For two blocks to remain together. So for two blocks to remain together, in contact, component of velocity or acceleration will be equal. So we can say here A2 cos theta 2. So let me mark the components in green color. So this is A2 cos theta 2 component perpendicular to the incline, perpendicular to this incline. And here it is A1 sine theta 1. So A1 sine theta equals A2 cos theta. So this is the wedge constraint equation. This is wedge constraint equation. So for the two blocks to remain in contact, the components perpendicular to the whatever is surface, they must be equal. So we can say the components perpendicular to surface for velocity and acceleration, they will be equal. So this is what we call as wedge constraint. So I hope you understood this topic of wedge constraint clearly. So let us see more examples of wedge constraint. Let me draw in some other color. Supposingly we have something like this. And we have a block here. Let us say this is block 1. And then we have another block. Let us say block number 2. This is block number 2. And this block 2 is kept on a fixed inclined plane. So this is fixed incline. Let us say this angle here is theta. Acceleration of this block 2 will be down the incline. Let us say A2. And acceleration of this block 1, let us say is A1 in downward direction. So these are the accelerations A1 and A2. Again, if we apply the same concept, components perpendicular to the incline, they are constant. So in that case, what will be the equation? So we can apply here, what is the component of A2? The component of A2 along this direction. So this angle here is theta. So it will be A2 cos theta. And this component here will be A2 sine theta. So components which are perpendicular, which is let us say A1, that will be equal to A2 sine theta. So A1, the component perpendicular to this surface, horizontal surface here. So A1 is perpendicular to this horizontal surface, and A2 sine theta is also perpendicular to this horizontal surface. So these two components are equal. So we can say by wedge constraint, A1 will be equal to A2 sine theta. So this is the equation of wedge or normal constraint. For the two objects to remain in contact, the components perpendicular to the surface, they should be equal for velocity or acceleration. So using this concept, let us take some examples. So let us move on to illustration 29 of our textbook. So illustration 29 of our notes. So class notes, illustration 29. Now we have a wedge here. So let me first draw a wedge. So this is a wedge which I have. And on this wedge, I'll place a mass. So the mass of the wedge is capital M and mass of the block on it is small m. Small m is the mass of the block and mass of wedge is capital M. And this is angle theta. So in this case, let us consider a block of mass small m is placed on a inclined surface of a wedge as shown in the figure. So we have to calculate the acceleration of the wedge. So as this block moves in downward direction, there will be a push on the wedge towards left. Let us say we consider this wedge motion towards left. Wedge will move towards the left side, whereas the block will move down the incline. So I hope you understand this concept clearly. In this case, the block, it will move down the incline, and the wedge, it will move in backward direction. So this is a movable wedge. This is not a fixed wedge. In this case we are considering movable wedge placed on the ground. This wedge is placed on the ground, and this wedge is movable. So let us see how we apply constraint equation here. So after some time, if I think, so what will happen? So let us say we consider this initial position and final position of the wedge. For better understanding, let me show it again. So suppose I show the initial condition and the final position. Suppose this is the initial position in blue color. So this is the initial position. Okay. Now, supposingly, I draw the wedge as well. Block on the wedge is like this. Just place on the top side. Now, because of this push of mass small m, what will happen? This wedge, it will move in backward direction. So let me show the new diagram of the wedge in red color. This is the new diagram of the wedge in red color. And the block has moved in downward direction. So let me show the block motion in downward direction. So this is the new position. Red color is the new position. So let me mark it. This is the new position. And this was the old position. And this angle here is theta. So in this case, let us think how much has this block moved. This block has moved by some distance down the incline. Let us say x distance, small x. And this wedge has moved some distance in left direction. Let us say capital X. Capital X is the distance moved by the wedge. Small x is the distance moved by the block in downward direction. So let me try to relate these two. So in this case, if I consider, let us say the relation between small x and capital X. So how are they related? So let me show that relation. Let me draw the diagram here. So in this case, we can say like this. So distance moved by the block in down the inclined direction. The block has moved some distance y in this direction, y. So now if I draw a triangle, so this will be y, and this distance, so let us show this distance properly. This distance will be x, capital X, and finally this distance will be small x. And this angle here will be theta. So this is our angle theta. I hope this is clear. Small x is this distance, which I have shown in this triangle. This is angle theta. And capital X is this horizontal distance, which I have shown here, horizontal distance, capital X. And this vertical distance between the center of mass of the block is y. So from this, if I try taking sine theta, so sine theta will be opposite upon hypotenuse, so y upon x. So we can say y equals x sine theta. So we can say velocity in y direction is velocity along x direction into sine theta. Similarly, on differentiating once more, so this comes on differentiating once, this comes on differentiating second time, so a sine theta. Let us consider the acceleration of wedge is capital A, acceleration of block in y direction, because block has two accelerations. One acceleration is in x direction, another acceleration is in y direction. So the acceleration of block in y direction, ay, equals capital A sine theta. Where what is capital A here? Capital A refers to the acceleration of the wedge in left direction. So let me show this. Acceleration of wedge in left direction is capital A. And acceleration of the block in y direction, let me show here. Acceleration of the block in y direction. So this is small a subscript y. So between relation between small a subscript y and capital A is given by ay is equal to a sine theta. So I hope you understood this analysis fully. Other than that, we will apply Newton's law equation. So Newton's law equation, so this is mg force, normal reaction n, and the component of mg perpendicular to the incline mg cos theta. So acceleration in y direction ay. So our Newton's law equation will come out to be big force, which is mg cos theta, minus small force, normal reaction, equals m into ay. This is Newton's law equation on the block. Finally, if I consider the Newton's law equation on the wedge, so in that case, what will be the equation? So in that case, we can say ay. First of all, let us substitute this value of ay. Ay will substitute. So mg cos theta minus normal reaction is m into a sine theta. So this is the Newton's law equation on the block of mass small m. Other equation, in this case, if I simplify, we have other equation as n sine theta equals mass of wedge into acceleration. How do I get it? So let us think about this forces on the wedge in horizontal direction. So for the wedge, we have normal reaction. Its component, normal reaction component. So let us think this angle is theta. So this angle will be theta. So this component of normal reaction here will be n sine theta. So n sine theta, that will be equal to mass into acceleration of the wedge. So we have two Newton's laws equation. Equation 1 for the block, equation 2 for the wedge, and third equation by constraint equation of wedge constraint. So using these three equations, we can solve for acceleration of the wedge. So on solving, we'll get the acceleration of wedge as, so acceleration of the wedge capital A, it will come out to be mg sine theta cos theta, the whole upon m plus small m sine square theta. So this is the procedure which we'll apply for wedge constraint. So let me show you once again how we will apply wedge constraint. So as I said, we have one wedge here. So this is the wedge initial position. Wedge mass is capital M. And we have a block which is placed on the wedge. Now, this block will slide down the wedge. And what will happen? So we will have a new position and initial position for this wedge. So suppose this angle is theta. Mass of wedge is capital M. Mass of block is small m. So let us see the initial and final position of the wedge. Let us show initial and final. So suppose I first draw initial position, let us say in blue color. So this is the initial position of the wedge, and initial position of the block is in upper part. Now, as this wedge moves down, there will be a push on the wedge in backward direction. So what will happen? So due to this, the wedge will move in backward direction. I am showing the new position of the wedge in red color, like this. And the block would have moved down by some distance, let us say y. So let me again show the distance. Center to center distance is y. Center to center distance between what and what? Between the two centers. So this is y. And the wedge has moved some distance, let us say x, in horizontal direction. So I'm showing it by capital X. Finally, talking about the displacement of the block along the incline. Let us say it is denoted by small x. So this is denoted by small x. And this is angle theta. Now, if I want to derive the relation between small x, capital X, and y, I will use the triangle. Let me show the triangle. This is small x, this is small y, and this distance, horizontal distance, is capital X. So this is y, and finally this is horizontal distance is capital X. Capital X here, small x here, and y here. And this angle is 90, this is theta. So y we have to find out. Let us say sine theta in this triangle, which is opposite upon hypotenuse. So y comes out to be capital X sine theta. So differentiating, we get velocity in y direction equals velocity in x direction into sine theta. Similarly, differentiating once more, acceleration in y direction is acceleration of the wedge, which is capital A, in horizontal direction into sine theta. So this is the equation for wedge constraint. So let me write the equation for wedge constraint. Ay equals capital A sine theta. Now, let us think about the free body diagrams. So forces acting on the small m and capital M. The first force which I'll mark is normal reaction, then mg for the wedge as well, and normal reaction by the ground also we can mark here in upward direction. Let me mark it in upward direction, normal reaction. So let me write capital Mg in downward direction, normal reaction N2 by the ground in upward direction, or let us say it is N1. Let us say this is N1, normal reaction N1. Also here we have normal reaction N by the incline on the mass, capital N. Again we will have Mg for this block. Acceleration of the block along y direction Ay, and the component of Mg. If I take the component of this Mg perpendicular to the incline for this block, so it will be Mg cos theta. And Newton's law equation, if I write for block of mass small m, it will be Mg cos theta minus normal reaction is May. And for the wedge, we have, this is the normal reaction. If I draw the free body diagram of the wedge here, so we will have normal reaction by the block on the wedge N. Its component in horizontal direction will be N sine theta, and the component in perpendicular direction, it will be N cos theta. This is n sine theta, and this component here will be n cos theta. So n sine theta leads to acceleration A. So our equation will come out to be, for the wedge, n sine theta equals mass into acceleration of the wedge in horizontal direction. For vertical, the force balances are equal. N cos theta equals n cos theta plus mg equals n1. So they are balanced. So I will not write that. And wedge constraint equation, we have ay is a sine theta. These are the three equations which we need to solve. So on solving these three equations, we will be able to find the acceleration of the wedge. And it will come out to be mg sine theta cos theta upon capital M plus small m sine square theta. So this is how we use wedge constraint. So I have explained you in detail how to use wedge constraint. Now let us move on to our next topic, which is wedge and pulley constraint. So in this case, we have both a wedge and a pulley. Wedge and pulley constraint. So in this case, let us consider the diagram first. So suppose we have a wedge here, and on this wedge we have a pulley. There is a pulley here, and this pulley is connected by a thread. Let us show the thread in the red color. This is the thread. Like this. Suppose this thread is connected directly to the wall. There is a wall here. This is the wall, and this is the ground. And this thread on other side is connected to a block. This is the diagram which we have. Okay. So in this case, let us consider the mass of the block as capital M, mass of the block as small m. Sorry, mass of block is small m, and mass of wedge is capital M. And this angle of the wedge is theta. Okay. Now in this case, what will happen? This block of mass small m will move downward, and the wedge will go in backward direction. This is obvious. Everyone will understand this. The block on the wedge, it moves down the incline, and the mass or the wedge, capital M, it moves in left direction. We have to find the relation. So in this case, let us try to find the relation. In this case, again, if I think about the previous situation, if I draw the triangle as we draw before, so this is y direction along which this block will move down. The wedge covers some block of mass small m. It covers some distance y, let us say, and it also leads to motion of the wedge in backward direction, which we showed as capital X. And we also have x, small x. Small x is the displacement of the block along the incline. So these are the relation, and this is angle theta here. So as in previous case, this relation will still be there. So this triangle will still be there. But in this case, what will happen? So in this case, if we think about the diagram, so let us think about the diagram. So let us show the initial position of the wedge and pulley system by red color. So this is the initial position. Initial position is something like this. And we have a pulley here. And initially the block was somewhere, let us say here. So this is the initial position, this angle theta. Now, after some time, what will happen? The wedge will move in backward direction. So let us say this pulley would also connected to wedge. It will move in backward direction. This pulley here moves in backward direction. And this wedge has moved in backward direction. And the mass has moved in downward direction. The mass is now somewhere downward position. like this. So this is our wedge, new position of the wedge. So in blue, I am showing new position of the wedge. In red, I have shown the old position of the wedge. And this angle is theta, as we already discussed. So this angle will also come out to be theta. So now, in this case, if I consider this distance, capital X, which I have shown here, capital X. So then we can say in perpendicular direction, like this, if I consider. So if I consider the perpendicular direction here, from here to here. So by geometry, I can prove. So this, if this angle is theta, this angle will also be theta. And by geometry, I can prove this thing, this distance comes out to be x cos theta. So this is x cos theta. So this distance is x cos theta, the perpendicular distance, x cos theta. So this is x cos theta. And now if I apply length constraint, if you remember we have used length constraint. Why will we use length constraint here? Because in this case, this is length L1, this is length L2. In this case, L1 plus L2 is constant. So L1 plus L2 is what? Constant. So if I consider L1, this point is fixed. So for L1, we will have 0. And after that, we will have what? Let us consider the accelerations. Let us consider the acceleration of the block AX in downward direction. And we also consider the acceleration capital A of the wedge in backward direction. So we have to find the relation between AX and X. Also, we'll consider acceleration AY, which is perpendicular to the surface. In the previous case, we already proved AY is equal to A sin theta. So that will still hold true. AY will be equal to A sin theta. From this triangle, we can prove again AY is A sin theta. Now, we are concerned here with the acceleration along down the inclined direction, AX. So for that, I am applying length constraint equation. So L1, it is fixed at this point, and this point is on the movable pulley. So in this case, where is this pulley moving? Pulley is moving in backward direction with acceleration capital A. So pulley is moving in with acceleration capital A in backward direction. So I can say due to that, the length of the string decreases. So I can say minus capital A. So here we will have minus capital A. So this is the thing for L1 plus L2. So this point here, let us consider this point for L2 and this point for L2. So if I consider these 2 points, so this point is moving with acceleration AX in down the inclined direction, leading to increase in length. So this will be plus AX. And this point. So this point we will have an acceleration which will be the component of capital A. So capital A is in this direction. So component of capital A along this direction will be what? So it will be A cos theta. So A cos theta. And this component A cos theta is in this direction. So we can say, so plus AX. So let us consider for L2. These are the 2 points. One point clearly leads to increase in length of L2. So plus AX. Now we want to find the value of AX in this case. So what will be the case? So in this case, we will have A cos theta. So what will be the A cos theta? What will be the sign of this A cos theta? As I already told you, acceleration is A, its component is A cos theta. Now that leads to increase in length L2, because this A cos theta will lead to increase in length of L2. Because where is this A cos theta? So A cos theta is in this direction, up the incline. So acceleration component is up the incline, leading to increase in length. So plus A cos theta. Now derivative of constant is 0. So this is for L2 and derivative of constant is 0. So I can say from this AX is A minus A cos theta. So AX comes out to be A bracket 1 minus cos theta. So this is the wedge constraint equation, wedge pulley constraint equation. So I hope you understood this clearly. This is slightly difficult, so let me show once more. So for those who didn't understand previously, again, let us see once more. So we are seeing pulley and wedge constraint. This is slightly difficult, so I'm repeating once again. Pulley and wedge constraint. So in this case, what do we have? We have a diagram. First, let us consider the diagram. Let us say we have a wedge like this, and there's a pulley here, and this is connected to a block of mass small m, and we have a string here which is connected to a wall. Now, this is the initial diagram. So what will happen? As the block slides down, this wedge will go in backward direction. Wedge has mass capital M. So let us again draw the diagrams. Let me show the initial position of the wedge. The initial position of the wedge I am showing in red color. This is the initial position of the wedge. In this case, the block is on the top. So this is the block of mass small m, and it is connected to a pulley, which is connected to a string to a wall. After some time, what will happen? So let us show the new position of the block. So this wedge would have moved to a new location. This is the wall still here itself. And we have a diagram like this. This is angle theta. This will be angle theta. The block would have moved down by some distance, let us say 1. And this wedge has moved some distance, capital X. And along the incline, it has moved, let us say, X distance. Small m has moved X distance. So again, if I draw the triangle, this is small x, this is y. Let me draw the diagram again. The triangle I will make once more. So first, let us show this capital X. This is capital X. Then we have this small x, which is like this. And we have this y. So this is the y displacement. So again, this angle is theta. So again, we will have sine theta is equal to y upon x. So y is equal to x sine theta. So ay is equal to capital A sine theta on differentiating 2 times. This is the previous relation. Now, let us consider acceleration in x direction. So for that, we will use length constraint. So let us consider the initial length of this side is L1, then this is L2. So length constraint says L1 plus L2 is constant. Let us talk about L1. This is one point, this is another point for L1. So first point is fixed to the wall, so 0. Second point, it moves in backward direction. So backward direction means what? Acceleration will be negative. Let us see. So this point moves in backward direction with acceleration capital A, leading to decrease in length of L1. So minus capital A. Plus this point here. This point here is moving with acceleration A in backward direction. Its component along the incline will be A sine theta. Sorry, A cos theta. So component will be A cos theta. So capital A cos theta here. This will be the component. Let me draw it slightly in a better diagram. This is A cos theta, which is the component in this direction. Now this leads to increase in length of L2. So increase in length of L2 means we will have plus A cos theta, plus A cos theta. Then this point here is moving with acceleration AX in downward direction. So plus AX. So this is about L2. Now derivative of constant is 0. So from this I can get AX is A minus A cos theta. So AX comes out to be A bracket 1 minus cos theta. So this is our final answer which we have in this case. This is our final answer. AX is A into 1 minus cos theta. So I now hope you are familiar with this idea of wedge and pulley constraint completely. So this is about the wedge and pulley constraint. So let us see some examples based on this. So our first example, let us take. In this case, illustration 30. We are considering illustration 30 of our class notes. So in it, we have to have the same situation. We have a wedge like this. Slightly made this on that diagram. Let me rectify. This is the wedge, capital M mass. On it, we have a block of small m mass. Angle is theta, and the surface is smooth. And this is the horizontal ground. Then we have a pulley here, which is fixed, and this string, which is further connected to a wall as shown. So in this case, we have to find what? Acceleration of the wedge. So acceleration of the wedge means capital A. So you symbol which we used is capital A. So let us use the relations that we learned. AY is equal to A sine theta. AX is equal to A bracket 1 minus cos theta. So now you all know this is AX, this is AY, and this is capital A. So let us try to find the value of acceleration. First of all, tension will be in up the inclined direction. Mg force can be resolved into mg cos theta perpendicular to the incline, mg sin theta down the incline. Normal reaction will act perpendicular to the incline. So if I write Newton's law equation, it will be like this. Newton's law equation for the block, we will have mg sin theta minus t is equal to max. Ax value we already know. This is Newton's law equation. Now, if I consider for the block, so in this case, for the block in perpendicular to inclined direction, so we will have mg cos theta minus normal reaction is may, which is nothing but ma sin theta, because from first equation we know ay is a sin theta. So this is one equation. So these are the equations for the block. For the wedge, let us think about the equation. So for the wedge, if I consider our equation will be, in this case, we will have tension force T minus, we will have, so tension force T will act on the wedge in this direction. Other than this, we will have tension force component, which is like this. So we'll consider tension minus T cos theta plus M. If I consider T, let us think first of all, how many equations do we have? So we have in this case tension T as the unknown. We have AX as the unknown, AY as the unknown, and capital A as the unknown. So we already have 4 equations. 1, 2, 3, 4. So what we already have 4 equations. So 4 equations and 4 unknowns. AX, AY, capital A, and tension. These are the one more normal reaction is also unknown. So we'll need one more equation. So one more equation we'll get by wedge. So wedge, we have one force which is T, and we have T here. Its component along horizontal will be T cos theta. So for the wedge, let me show the diagram. This is like this. First of all, on the wedge, we have a pulley, and there is a tension force like this. Also, there is a tension force in this direction. But the component of tension in horizontal direction, this angle is theta because this angle is theta. So that the horizontal component will be T cos theta. So T minus T cos theta, and other than that, there will be normal reaction N on the wedge. So its component along horizontal will be N sin theta. So we can say, let us again draw this diagram so that you understand better. So let us consider the diagram of the wedge. This is the wedge. On the wedge, we have normal reaction due to the block. And if we think about the geometry, it is like this. So if this angle is theta, angle between two lines is angle between the perpendicular. So this angle will come out to be theta. Okay. Now this component will be n sin cos theta because it is along theta. This is n cos theta, and this component will be n sin theta. Other than this, we have a tension force T on the wedge. So T like this, and one T here. So its component along horizontal will be T cos theta. T cos theta. Other than that, we have the acceleration of the wedge A in backward direction. So Newton's law equation will come out to be P plus n sine theta, which are in backward direction, minus P cos theta, which is in forward direction, equals mass of wedge into acceleration of wedge. So our Newton's law equation for the wedge will come out to be P, which is in forward direction, plus n sine theta, which is also in forward direction. So P plus n sine theta. For it is both are in backward direction. Sorry, P which is in backward direction and n sine theta, which is also in backward direction, minus P cos theta, which is in forward direction. That equals mass of wedge into acceleration of wedge. So this is the fifth equation that we need. 5 equations, 5 unknowns. So from these equations, we can find the value of acceleration. So acceleration A of the wedge will come out to be mg sine theta upon capital M plus 2m bracket 1 minus cos theta. So this is the answer to this question, illustration 30. So now let us move to next illustration, which is illustration 31. In this case, we have a rod which is having some mass, let us say small m, and this rod is constrained to move between these walls, let us say. So this is our rod. This is our rod, and these are the walls. Now this rod is placed on an inclined plane, which I'm showing in brown color, let us say. It is given that the wedge of mass capital M and the rod, they are in contact at all times. So in this case, we have to find the acceleration of the rod and the wedge. So this rod is going to move in downward direction and this wedge is going to move in backward direction. So let us consider in this case, the acceleration of wedge is capital A and the acceleration of rod is small a. Let us find the relation between small a and capital A. So suppose this rod moves small x distance, then this wedge moves capital X distance. So let us find the relation between small x, which is this, and capital X, which is in horizontal direction. So this is the triangle which we have. So this is the relation. Okay, small x, capital are related like this. So for understanding how we get this, let us see the diagram. So let me draw the diagrams of the wedge in a better way. So let us show the initial and final position of the diagram. So in this case, let us consider this is the initial position. This is the initial position. This is our rod and the balls, you understand, then they are there. Now, after some time, what will happen? This wedge will have moved somewhere in other position. Let us show the new position in blue color. It's like this. Slightly, I need to make a better diagram. Let us say this is the new diagram. Yes. Now, in this case, the wedge would have moved towards left and the rod would have moved down. Okay, so this is the case. Now, in this case, let us consider the distance moved by the rod as small y or small x. Small y or small x. So this is small y. Let us say if I consider this distance as small y. Okay. And the horizontal distance in this case is capital X, distance moved by the wedge. So capital X. And this angle, if you see carefully, this is nothing but theta, the angle of the wedge. Theta. What is the relation between y and x? So let us take in this case tan theta. So tan theta will be opposite upon adjacent, y upon x. So y is x tan theta. So differentiating, we can say acceleration of the rod is equal to acceleration of the wedge into tan theta. So our equation turns out to be small a is equal to capital A tan theta. So this is the equation which we'll get if I apply wedge constraint here. This is one equation, which is wedge constraint equation. Now, in this case, let us think about Newton's law equation. So Newton's law equation in this case will be like this. So if I first consider the rod, so for the rod, we have mg force in downward direction. We also have the normal reaction n perpendicular to the incline. Its component in upward direction will be n cos theta, because this angle is theta. Angle between two lines is angle between perpendiculars. So this is n cos theta. So in the vertical direction, I can say mg, the downward force on the rod, minus n cos theta, upward force on the rod, is equal to mass of rod into acceleration of rod in downward direction. So this is the Newton's law equation for the rod. Now, after writing Newton's law equation on the rod, let us think about wedge. So for the wedge, what are the forces acting? One is normal reaction N. The normal reaction is N in this case. So other than that, we have on the wedge mg, capital M into G. Other than that, we have acceleration capital A of the wedge. So if I consider the component of this normal reaction, so in N will have two components. So along vertical direction, what is the component? So it will be n cos theta in vertical direction and n sin theta in horizontal direction. So we can say n sin theta in horizontal direction, the component n sin theta on the wedge, it leads to acceleration as in previous case ma, and along the vertical we have normal reaction by the ground, let us say n1, which is in upward direction, that equals mg plus n cos theta in downward direction. So these are the equations on the wedge. I hope you understood this. On the wedge, we have one force, which is N1 by the ground on the wedge in upward direction, n cos theta, which is the component of normal reaction by rod on the wedge in downward direction. And we have mg, mass of wedge into gravitational acceleration in downward direction. So these are the equations that we have. On solving these equations, we will get the capital A value. On solving, capital A will come out to be mg upon m tan alpha plus m cot alpha. Sorry, theta. In this case, I have considered the angle of inclination as theta. I can write capital A acceleration will be theta. So this is how we solve illustration 31. So I hope you understood this wedge constraint fully. Now let us move on to general constraint. Let us now see general constraints. So in general constraint, let us see illustration 32 of our class notes. So in this case, we are given wall, which is shown like this, and we have a rod of length L. So this is a rod of length L. Let us say A and B are the points, and L is the length of the rod. Suppose this horizontal distance is X and this vertical distance is Y, and this angle here is theta. So in this case, we have to find the relation between velocities. Suppose this point has velocity u, then what is the velocity of this B point? That is the question. The question says, if this lower point has velocity u, then what is the velocity of this point B, other end point? So we have to find the velocity of this end point, VB. So let us see how to solve this question. In this case, we have various methods to solve this question. So let us see first method. So first method uses Pythagoras theorem. X square plus y square is L square. So on differentiating, we have 2x dx by dt plus 2y dy by dt. L is a constant, so its derivative will be 0. So 2x into vx of point A plus 2y into VB, velocity of point B. equals 0. So 2 cancels. And from this we get x Vx is equal to, or Vx, we can write velocity of A itself. Instead of Vxa, we can write Va itself. So let me write Va is equal to minus of YVB. So in magnitude, we can say x into u is equal to y into VB. Now, from this, I can say VB equals u into x upon y. Now, from this diagram, what is x upon y? It is cot theta. So we can say our answer will be VB is u cot theta. Our answer is VB is u cot theta. So this is one method which we use. X square plus y square is L square. Differentiating 2x dx by dt plus 2y dy by dt equals derivative of constant, which is 0. So after that, dx by dt we can write as VA because it is velocity of point A in horizontal direction. So 2x VA plus 2y dy by dt is VB. So VB we can write. Now considering the magnitude x VA is equal to y VB magnitude wise. So from this VB is u x upon y. How did I write this u here? Because velocity of point A is given as u. So VA is nothing but u. So hence x u is equal to y UB. So instead of VA, I have substituted u. So VB comes out to be u into x upon y. But from this triangle, if I take cot theta, it will be x upon y. So x upon y I substitute as cot theta. So this is one method to solve this kind of question. Now, another method to solve this kind of question is component of length. So component along the length are equal. So component of velocities or accelerations along the length are equal. So this is a slightly quicker method. Let us see the method. So this is our rod, and we have the velocity, which we show like this. Let us say velocity at point B, I'm showing like this, and velocity at point A is this, u. So this here is u, whereas this here is VB. And this angle here is given to us as theta. Now, if I consider this angle as theta, because they are opposite angles, the component of u will be u cos theta. And if I consider this angle as 90 minus theta, by geometry, we can easily prove this angle will be 90 minus theta. So this is 90 minus theta. So component of VB will be VB cos of 90 minus theta. Now, if I equate the components along the length, this is the component of VB, along the length, this is the component of u. So if I equate the components of velocities along length, so it will be VB cos of 90 minus theta equals u cos theta. So VB cos of 90 minus theta is nothing but sine theta. So this is equal to u cos theta. So VB comes out to be u into cos theta upon sine theta. Cos theta upon sine theta is cot theta. So VB is u cot theta. So this is our relation. VB is u cot theta. So by using another method also, we can prove that component of velocities or acceleration along the length are equal. So by using the same method, we can have what? VB is u cot theta. So this is how we prove VB is u cos theta by using component method. Component of velocities or acceleration along length are equal. Now let us use this in illustration 33 as well. So in illustration 33, we are given a pulley which is connected to mass M2, and another end is connected somewhere here, and this point is moving with velocity v1 in horizontal direction, and this is m1 and on the ground. This is a velocity v2. So now, as we discussed in previous example, the components of velocity along length are equal. So in this case, what method I will use? Components of velocities along the string are equal. Along string are equal. So let us consider this string. So if I consider the components of velocity along string, they are equal. So v2. So v2 is the component which is already along the string. And v1, if I consider this component of v1 along the string, so we will have a component of velocity along string, which is this component. So what is angle theta? This is angle theta. So this angle will be theta. So this will be v1 cos theta. So I can say v2 component of velocity along string equals v1 cos theta, component of velocity along string. So v2 is v1 cos theta. So we have proved v2 is v1 cos theta because v2 is what? The component of velocity along the string. v1 cos theta is what? v1 cos theta is also the component of velocity along string. So we are equating the components of velocity along string because they are equal, because the string is considered inextensible. We consider string as what? Inextensible. So this is the method which we'll use here. Other than that, we can also use again the geometrical approach of setting up a geometrical equation and then differentiating to get the same relation. But in this case, this gives a faster answer. So let us use this method. Now, moving on to our next question, which is illustrative example 34. So in 34, we are given a diagram, which is something like this. We have a block M2 here, and this is connected to a wall here. Now, this is M1. So we have this ring here, which has mass M1. So ring and block M2, they are held in position as shown in the figure. So this is the figure. So this is the ground. Now, what happens is the system is released and M1 is greater than M2. So in this case, we are given M1 is greater than M2. So M1 will move down, M2 will move up. So after some time, what will be the diagram? So after some time, the diagram will be something like this. The ring would have moved down, M1 would have moved down, and this string would be something like this. And this is the pulley, and this is our M2 block. This is the new diagram. So let us consider the velocity of the M1 mass as V1 and velocity of M2 mass as V2. So V1 and V2 have you understood. So now let us use the component method. So components of velocities or acceleration along the string are equal. So in this case, V2 is already along the string. So V2 is already along the string. Let us take the component of V1 along the string. So let us do some geometry here. So in this case, let us consider this angle is theta. So this will be V1 cos theta. We can say V2 is equal to V1 cos theta by this component of velocities along string are equal method. So we can say by string, in this case, this method, by this method, components of velocity along string are equal. We can say V2 equals V1 cos theta. So this is how we'll solve this illustration 34. So after this, we will take our next topic, which is spring force. So after this, we'll move on to our next topic, spring force, in our next section. So stay tuned, we will go ahead.